Welcome to the Deep Dive. We're all about getting you straight to the heart of complex topics.
Helping you understand things efficiently.
Exactly. And today we're diving into something pretty mind-bending, how artificial intelligence actually learns physics.
And not just learns, but whether different AIs trained on the same stuff actually agree on the theories they come up with.
Right, it's based on this really interesting paper from MIT. Do two AI scientists agree on physics? It came out April 3rd, 2025.
And it pushes this idea beyond AI just being a tool, right? It's exploring AI as potentially an autonomous scientific discoverer.
That's the core of it. So our mission today, understand how these AI scientists, they use a system called mass, how they build their understanding of physical laws.
And critically, does their learning process show us anything new, anything innovative about how scientific theories are formed?
Okay, so let's start with these AI scientists. What exactly are they in the context of this paper?
Well, think of them as machine learning models, but specifically designed to mimic parts of the scientific process so they can formulate hypotheses, suggest experiments, interpret results.
All with minimal human help.
That's the ambition, yeah. Moving beyond AI just crunching numbers we give it, towards AI actually driving the discovery process itself.
And the paper suggests these kinds of end-to-end platforms are starting to emerge, ones that might discover physical laws on their own.
Exactly. It's still early days, but that's the direction this research is pointing towards, this idea of AI not just fipping data to equations we already know,
But actually finding the underlying principles.
precisely finding those principles directly from the observations. That's the potential innovation here.
Which brings us to the big question. Do they agree? If you have multiple AIs learning the same physics, do they land on the same theory?
Or do they innovate? Do they come up with different, maybe equally valid ways to explain the same thing?
It kind of reminds you of science history, doesn't it? Like Newton and Leibniz both inventing calculus independently.
That's a great parallel the paper draws, yeah. Different approaches, different notations, but ultimately describing the same core mathematical truths.
So the researchers wondered if AI might do something similar. Independent discovery, maybe even different theoretical styles for the same physics.
And to test this, they couldn't just grab any AI model off the shelf.
No, they built something specific. Tell us about MASS.
Right. MASS stands for Multiple AI Scalar Scientists. It's a novel neural network architecture they developed.
Okay.
And the key idea, the real innovation with MASS, is its ability to learn from multiple different physical systems and unify that information within one single network. It does this by learning a scalar function for each system.
A scalar function, like a Lagrangian or a Hamiltonian, that kind of concept.
Exactly like that. It's learning this sort of high-level unified description that captures the fundamental dynamics rather than jumping straight to the equations of motion.
So it's learning the underlying essence of the system first.
Precisely. And here's a really clever part, another innovative bit. MASS has a shared final layer in the network. This layer is shared across all the different physical systems it's learning about.
Okay, shared layer. What does that do?
It takes the derivatives of those learned as scalar functions, the Lagrangians or Hamiltonians it figured out, to actually infer the specific equations of motion for each system.
Ah, I see. So that shared layer forces it to look for consistency, for a common framework.
You got it. It pushes the AI towards finding a single, consistent theoretical framework that can explain all the different physics it's seen. It's aiming for a generality, for a more fundamental theory.
Like finding one rule book that explains springs, planets, everything. Okay, so walk us through how MASS actually works. What are the steps?
Sure. The paper lays out a four-step workflow. First, obviously, data ingestion. It gets observational data, the raw facts from different physical systems.
Like experimental results?
Yep. Second, hypothesis formation. For each system, a part of the network learns that unique scalar function we talked about, trying to capture its specific dynamics.
Okay.
Third, theory evaluation. That's where the shared final layer kicks in. It does the math, takes the derivatives, and spits out the inferred equations of motion for each system. That's the AI's theory.
Right.
And finally, step 4 is refinement and generalization. The AI compares X theory's predictions to the actual data, sees where it went wrong.
Calculates the error.
Exactly, across all the systems. And then it uses backpropagation, the standard neural net learning method, to tweak both the individual scalar functions and that crucial shared final layer. The whole goal is to get better and better, finding one framework that works accurately everywhere.
That is really ingenious. It's not just fitting curves, it's genuinely trying to learn the underlying rules. So what happened when they tested this? Let's start simple. One mass scientist, one simple system, like a harmonic oscillator.
Okay, yeah, the simple harmonic oscillator, classic physics 101. And MASS did learn it successfully. It could predict the motion accurately.
But I sense a but coming.
Well, the way it represented the theory was unexpected, even with regularization, which usually encourages simplicity.
Uh-huh.
The learn it scalar function, which looked a bit like the Hamiltonian, the total energy, it ended up having a lot of terms, surprisingly many.
How many are we talking?
I think the paper mentioned something like 42 significant terms.
42. For a simple oscillator, wow, that's not the elegant FEMA or simple energy equation we're used to.
Not at all. It immediately tells you the AI's first pass at understanding might not prioritize human notions of elegance or simplicity. It might be exploring something much broader.
And were there other weird things about this learned function?
Yeah, a couple. It was convex instead of concave, which is typical for energy. It even had negative values sometimes. Again, not standard for how we write down energy.
So it works, but it looks weird to us. It suggests the AI might represent physics in non-standard, maybe even novel ways.
Exactly. It's exploring a different part of the theoretical landscape, you could say.
But with all those, 42 terms, were they all actually saying something different? Or was there overlap, redundancy?
Great question. And they checked that using correlation analysis. They looked at how these terms activated together.
Okay.
And they found that, yeah, many of these terms were actually strongly correlated. They seemed to be firing together.
So maybe it's not 42 completely independent ideas.
Probably not. It suggests that while the AI starts complex, many terms might just be different mathematical facets of the same underlying, maybe complex, learned concept, like different ways to phrase the same core idea in the AI's developing mathematical language.
Okay, so one AI, one simple system, learns it, but maybe in a complex, non-intuitive way initially. What about learning multiple systems? Did exposing it to more complexity help it simplify or generalize? They fed it a sequence, right? Oscillator, pendulum, Kepler problem.
Yeah, up to a relativistic harmonic oscillator. So increasing complexity. And this is where it gets really interesting for generalization.
What did they see?
They saw a clear trend. As the single mass scientist was trained on more and more diverse systems, the number of distinct mathematical terms it needed to explain all of them actually tended to decrease.
Really? So more systems led to fewer core concepts. That sounds like it's finding more fundamental rules.
That's exactly what it suggests, a drive towards generality, towards parsimony maybe. It's forced to find explanations that work broadly, not just for one specific case.
Makes sense. It can't just memorize rules for each one. It has to find the common threads.
Precisely. But there was a neat twist, too.
Oh.
While the number of distinct building block terms went down, the specific ways it combined those terms to explain each individual system could actually become more diverse.
Okay, unpack that. Fewer basic ingredients, but more creative recipes.
Kind of, yeah. It's like it settles on a core set of fundamental concepts, but shows innovation in how it applies and mixes those concepts to fit the specifics of each different physical situation.
So convergence on fundamentals, but divergence or innovation in application. Interesting. Did they see a consistent core set of terms appearing across all systems?
They did. That was another key finding. When it had to explain multiple systems, mass tended to use almost the exact same core group of mathematical terms.
Which really points towards unification, right? It's finding mathematical structures relevant across different physical scenarios.
Definitely. It suggests it's latching onto something fundamental that links these seemingly different systems.
Okay, this is all super interesting with one AI, but the paper's title asks about two AI scientists agreeing. So what happens when you set multiple mass networks loose on the same problem? Do they converge?
Right. This is the direct test of the main question. They took multiple mass networks, gave them different random starting points, different initial guesses, you could say, and trained them all on the exact same physical system and data.
And the verdict? Agreement or disagreement?
The key finding was strong agreement, actually, despite the fact that the internal details of the networks, like the exact numerical weights or neuron activation levels, could be quite different.
Right, because they started randomly.
Exactly, but the significant terms each AI identified as being crucial for explaining the physics, those were remarkably consistent across the different AI instances.
So they might take slightly different internal paths, but they land on the same core concepts as being important.
That's what it looks like. They used PCA principal component analysis to dig into the internal states, the representations learned by the different AIs.
And that confirmed it.
Yeah, it showed a strong correlation between the internal representations. Even if the specifics varied, they were fundamentally capturing the same underlying physics. It indicates convergence towards a shared theory.
So the answer to do two AI scientists agree seems to be generally yes. at least in this setup.
Within this framework, yes, they tend to converge on the fundamental components of the theory when given the same evidence.
That's pretty profound. Suggests a robustness to the discovery process, maybe. Now, they didn't just stick to textbook problems, did they? They pushed maths with more novel synthetic systems.
They did, and this is where we see some really fascinating hints about innovation in the framework of physics itself. They designed synthetic physical systems with more complicated potential energy functions, stuff deliberately chosen to be outside the standard examples.
To really test its limits and see what kind of physics it preferred.
Exactly, and they specifically analyzed whether the scalar functions mass learned looked more like Hamiltonians, that's kinetic energy plus potential energy.
T plus V, right?
Or more like Lagrangian's kinetic energy minus potential energy, TV.
Two fundamental ways we formulate classical mechanics. Did the AI show a preference?
It did, and it was dependent on complexity. For the simpler systems, yeah, the learned descriptions often looked more Hamiltonian-like.
Okay, that seems intuitive, maybe.
But, and this is a big but, as they ramped up the complexity of these synthetic systems,
Yeah.
there was a clear, statistically significant shift. The AI's learned descriptions started looking much more like Lagrangians.
Whoa. So as things got trickier, the AI gravitated towards the Lagrangian framework, TV instead of T plus V.
That's what they found. It suggests the Lagrangian approach might be, in some sense, a more robust or general language for the AI to capture diverse physical dynamics, especially complex ones.
Why would that be? What's special about the Lagrangian approach from an AI's learning perspective, perhaps?
Well, that's a huge question this research opens up. Lagrangians work really well with generalized coordinates, which are super flexible for describing complex system configurations. Plus, the whole framework is based on the principle of least action.
A minimization principle.
Exactly, a global optimization idea. And neural networks learn through optimization, so maybe there's a natural affinity there. The AI is essentially doing optimization, and the Lagrangian is built on an optimization principle.
That makes kind of sense.
And they did further analysis constraint optimization, showing they could take the AI's learned network and pretty directly translate it into a Lagrangian theory with high accuracy, even for these weird, novel systems it hadn't seen before.
So it wasn't just vaguely Lagrangian-like. It was effectively learning Lagrangians.
It strongly points that way. It suggests Lagrangian mechanics might be a particularly powerful and general way for AI to figure out physics, almost like the AI is rediscovering its utility from scratch.
Without being told, use the Lagrangian.
Right, and they even tried this on harder stuff, preliminary work on chaotic systems like the double pendulum.
Which are notoriously complex.
Very. And even there, mass could reproduce the chaotic trajectories, and the theories it learned still resembled Lagrangian mechanics. And this is without explicitly building in things like energy conservation into the AI's design.
Wow. Okay, so let's try to bring this all together. What are the main takeaways from this deep dive, especially thinking about innovation?
Okay, takeaway one. AI scientists, like mass, seem to converge on the basic physics when given the same data. They tend to agree on the fundamentals. But their initial process might look very different from ours. They might explore complex, non-intuitive mathematical spaces first, using representations that aren't immediately elegant to us. That's a form of exploration, maybe innovation.
And then there's the Lagrangian finding that feels like a big potential insight, right?
Absolutely. That preference for Lagrangian descriptions as complexity increases is, well, it's fascinating. It suggests that maybe this framework is somehow more fundamental or at least more generalizable, even for an AI learning from scratch.
Could that be an innovative insight from the AI's learning process itself?
It could be. It highlights that AI might not just rediscover physics we know, but represent it or even prioritize certain formulations like the Lagrangian in novel ways that give us new perspectives. Think about the complex oscillator theory, the non-standard math. It's exploring.
But interpretability is still a hurdle. Yeah, can we actually understand these potentially complex, novel theories the AI comes up with?
That's the challenge, definitely. The raw output might be dense. But tools like analyzing the important terms or the constrained optimization they use to map things onto Lagrangians, those are promising directions. They help us peek inside the AI's reasoning.
So we're left with this really provocative thought, aren't we? This AI preference for Lagrangians.
Mm-hmm.
Does it hint at something deep about physics itself? Is the universe somehow inherently Lagrangian in a way that AI latches onto? Or is it just an artifact of the data, the model, the learning process?
Exactly. It forces you to wonder, is the AI showing us a bias in our usual way of thinking, or is it uncovering a deeper truth about the structure of physical law? It's a glimpse into how AI might change not just how we do science, but maybe even how we think about the fundamental nature of reality.
A lot to ponder there. A truly fascinating look at the intersection of AI and fundamental science.